In this video, we're going to talk about an application of the exponential distribution to waiting times. So suppose we have a scenario where particles are arriving independently. And suppose that lambda is the arrival rate. And let's say we're measuring the time period in minutes, so the lambda is the average number of arrivals per minute. So we've seen this situation before in connection with the Poisson distribution. So how is this related to the Poisson distribution? The number of arrivals per minute is approximately Poisson lambda. It has the Poisson lambda distribution, right? So if lambda was 5, for instance, then you can calculate the probability that there would be 7 arrivals per minute or 4 arrivals per minute, and so on. But in this scenario, we're interested in the waiting time for the next arrival. So let capital X be the waiting time for the next arrival. So this is something where we would want to find the distribution function, the density function of this random variable, right? So we want to be able to say, okay, what's the probability that x is between 5 and 8, or the probability that x is more than 7, right? The probability that you have to wait more than 7 minutes for the next arrival. So in this case, this is a continuous random variable. Okay. So we've formally defined a random variable to be a function, and so it's a bit imprecise to say that x is a random variable, but people say that this is a random variable anyway. I mean, what we want to do is we want to describe x in terms of a random variable, meaning we want to find some function that will tell us the probability that x is within some given bounds. Okay. So it turns out that x has an exponential distribution with parameter lambda. Okay, let's explain why this is true. So we'll find the distribution function, capital F of x. Let that be the distribution function of capital X. So first of all, we know that capital X is greater than or equal to 0 because the waiting time can't be negative. And so we know that capital F of little x is 0 if little x is less than or equal to 0. Right? Now what about when little x is positive? Well, by definition, capital F of x is the probability that capital X, what did I say? So for little x greater than 0, capital F of little x is equal to a probability that capital X is less than or equal to little x. And that is 1 minus the probability that capital X is greater than little x. Well, what does capital X greater than little x mean? Remember, we're describing capital X as the waiting time for the next arrival, right? So this probability is the probability that that you have to wait more than X minutes for the next arrival. Now, if you think about what that means, to have to wait more than X minutes for the next arrival, another way of phrasing that is that in those X minutes, there's no arrival. So we want the probability that there is no arrival in X minutes. Okay. Well, recall that the number of arrivals in X minutes the number of arrivals per minute is approximately the Poisson distribution. It is a discrete random variable with a Poisson distribution with parameter lambda. That's the number of arrivals per minute. So the number of arrivals in X minutes, right? Our time interval is X minutes. Well, if we have on average lambda arrivals per minute, then we have on average lambda X arrivals in X minutes. So this is a discrete random variable with a Poisson lambda X distribution. Okay. So there's something that I'm sort of sweeping under the rug is that we are using the Poisson as an approximation, but in this scenario, we're assuming that it actually does have a Poisson distribution in order to get a nice formula. So we assume that the number of arrivals in X minutes is a discrete random variable with a Poisson lambda X distribution. Well, then what's the probability that there are no arrivals in X minutes? That would be the probability that you have 0 arrivals in X minutes. And so we apply the Poisson distribution, right? This is when K is 0 to the Poisson distribution. So we get e to the minus lambda times lambda to the 0 over 0 factorial. That's e to the minus lambda. Oh, lambda x, sorry, because we have no arrivals in X minutes. And so that's e to the minus lambda x. And so capital F of x is 1 minus e to the minus lambda x for x greater than or equal to 0. Writing it out as a piecewise function, it would be, that's when x is greater than or equal to 0, and when x is less than or equal to 0, it's just 0. So that's the distribution function, and now we take the derivative to calculate the density function. That is going to be lambda e to the minus lambda x, or x for x greater than or equal to 0. So therefore, x does have an exponential distribution. Okay. So going back to what we had before, we're interpreting lambda as the arrival rate, the number of arrivals per unit time. But suppose that the number of arrivals, let's say that the number of arrivals is a half per minute. Okay. So, for example, half an arrival per minute. Well, if there's half of an arrival per minute, so on average 1 arrival per 2 minutes, then what would be the average waiting time? On average, there's 1 arrival per 2 minutes. So that would mean that on average you would have to wait 2 minutes to expect an arrival, right? So saying that there's half an arrival per minute on average is the same as saying that on average there's 2 arrivals, 2 minutes per arrival. So we can actually interpret 1 over lambda as the average waiting time. Okay. So going back to kind of the summary, so the summary is if particles arrive independently and capital X is the waiting time, for the next arrival, then capital X has an exponential distribution with lambda being the arrival rate, and that's equal to 1 divided by the average waiting time. So this is sort of the summary of what we've discussed. Here's an example. Let's say that phone calls arrive independently at an average rate of 2 per hour. What's the probability that you'll have to wait, the probability of waiting more than 3 hours for the next phone call? Well, we've seen that we have an exponential, the waiting time can be modeled by an exponential distribution. So let X be the waiting time between calls. Then we use an exponential distribution with parameter 2, right? Our lambda is equal to 2 because it's the average arrival rate. And we want the probability that X is greater than or equal to 3. So that's going to be the integral from 3 to infinity of 2e to the minus 2x. So that's equal to minus e to the minus 2x evaluated from 3 to infinity. And then when you evaluate the bounds of integration, when you plug in infinity, you get 0. So you get 0 minus negative e to the negative 6. So that's e to the minus 6, which is 1 over e to the 6, which is some really small number, right? Well, let's see, e is a bit more than 2, so your probability is going to be less than 1 over 64. but it'll be bigger than 1 over 3 to the 6th power. Okay. So anyway, that's the probability that you'll have to wait at least 3 hours for the next call.